Welcome dear friends to my channel. Today we will discuss the use of IC555 as an astable multivibrator. So this is the block diagram of astable multivibrator using IC555. As you can see that pin number 8 and pin number 4 are connected to VCC. The resistance RA is connected between pin number 8 and pin number 7. The resistance RB is connected between pin number 7 and pin number 6. Pin number 6 and pin number 2 are short circuited. The capacitor C is connected between pin number 6 and ground, and we can obtain the output at pin number 3. So this circuit shows the internal structure of IC555 connected in a stable mode. Here you can see that the three resistors of 5 kilo ohm each are connected in series, and a voltage VCC is applied across this series combination. So the voltage across each resistor is VCC by 3. This 1 and 2 are the comparators which compare the voltage of capacitor with respect to the voltage appearing at this non-inverting terminal and the inverting terminal. This is the RS flip-flop. T1 and T2 are the transistors. T1 is PNP transistor and T2 is NPN transistor. This NPN transistor is connected through resistance 100 ohm, and this is the NOT gate. So whatever is the Q bar, the NOT gate will produce inverted output at the output terminal 3 of IC555. Initially, when we switch on the supply, let us consider that the voltage across capacitor is Vc equal to 0 volt. Now as Vc is less than Vcc by 3, the comparator 2 output becomes high. Due to this, S becomes 1, and hence Q becomes 1 and Q bar becomes 0. Due to this, in the presence of NOT gate, the output becomes high. Further, as Q bar is 0, the transistor T2 becomes off. Now as the transistor becomes off, the capacitor starts to charge from VCC through RA and RB resistors till the voltage across capacitor just crosses 2 VCC by 3. As soon as the voltage across capacitor becomes less than 2 VCC by 3, the comparator 1 output becomes high. Due to this, R becomes 1, hence Q becomes 0 and Q bar becomes 1. As Q bar becomes 1, due to this NOT gate, the output becomes 0. Further, as Q bar is equal to 1, the transistor T2 becomes on. As T2 becomes on, the capacitor C starts to discharge through the resistance RB and the transistor T2. So the voltage across capacitor decreases exponentially. As soon as the voltage across capacitor becomes slightly less than Vcc by 3, then again the comparator 2 output becomes high, due to which S becomes 1, hence Q becomes 1, Q bar becomes 0, and due to this NOT gate, again the output at terminal 3 becomes high. Further, as Q bar is 0, the transistor T2 is switched off so that the capacitor again starts to charge through RA and RB till it reaches 2 VCC by 3. This way, the on and off cycle of the stable multivibrator continues as per the charging and discharging of capacitor between VCC by 3 and 2 VCC by 3. This figure shows the charging and discharging cycle of the capacitor corresponding to on and off time of the output at pin number 3. When the capacitor C is charging from VCC by 3 to 2 VCC by 3 through RA and RB, then the charging time is decided by the resistors RA, RB and C. Whereas when the capacitor is discharging through RB, at that time the discharging time is decided only by RB and C. At time t equal to 0, the voltage across capacitor is VCC by 3. So remaining 2 VCC by 3 voltage is responsible for the charging of the capacitor. So if we write the charging equation, we can say that Vc is equal to Vcc by 3 plus 2 Vcc by 3 times 1 minus e raised to minus t upon Ra plus Rb into C. Now at time t equal to t on, the voltage across capacitor becomes 2 Vcc by 3. So if we put t equal to t on here and Vc equal to 2 Vcc by 3, we get 2 Vcc by 3 equal to Vcc by 3 plus 2 Vcc by 3 1 minus e raised to minus t on upon Ra plus Rb into C. If we cancel Vcc by 3 from both sides, we get 2 minus 1 equal to 2 into 1 minus e raised to minus t on upon Ra plus Rb into C. So this gives 1 equal to 2, 1 minus e raised to minus t on upon Ra plus Rb into C. If we bring this 2 on this side, we get 1 half equal to 1 minus e raised to minus t on upon Ra plus Rb into C. If we bring this term on the other side and 1 half on this side, we get e raised to minus t on upon Ra plus Rb into C equal to 1 half. If we take inverse on both sides, we can write e raised to minus t on upon Ra plus Rb into C equal to 2. So if we take ln on both sides, we get t on upon Ra plus Rb into C equal to ln2, which is 0.693. So this gives us the value of t on as 0.693 times Ra plus Rb into C. At t equal to t on, the capacitor is charged up to 2 Vcc by 3. Now the capacitor starts to discharge through the resistance Rb during time interval t dash equal to 0 to t off as Vc equal to 2 Vcc by 3 e raised to minus t dash upon Rb into C. At time t dash equal to t off, voltage across capacitor becomes Vc equal to Vcc by 3. So if we put these two values in this equation, we get Vcc by 3 equal to 2 Vcc by 3 e raised to minus t off upon Rb into C. So this gives 1 equal to 2 into e raised to minus t off upon Rb into C. Hence 1 half equal to e raised to minus t off upon RB into C. Taking inverse on both sides, we can write e raised to T of upon RB into C equal to 2. If we take ln on both sides, we get T of upon RB into C equal to ln 2, which is 0.693. So this gives T of equal to 0.693 times RB into C. So the off time is decided by RB and C. Now the total time period of one complete clock cycle is T equal to T on plus T off. If we add the values of T on and T off, we get total time period as 0.693 Ra plus 2 Rb into C. And the frequency of clock is f equal to 1 upon T, which gives 1.44 upon Ra plus 2 Rb into C. So this is the frequency of clock pulses generated by IC 555 in astable mode. Now we can calculate the percentage duty cycle as on time upon periodic time multiplied by 100%. So if we put these values, we get the duty cycle as 0.693 Ra plus Rb into C divided by 0.693 Ra plus 2 Rb into C into 100%. So C will cancel out and this will cancel out. This gives Ra plus Rb upon Ra plus 2 Rb into 100% as the percentage duty cycle of the astable multivibrator. And this shows that this is not a perfect square wave. So thank you for watching.